For this last lecture, I will just want to give some survey, some overview, what can be done with these easy quantum groups. So not much of details, but just some remarks, and I will give some references, and if you want, you can read it in the article. Of course, you can also ask me and we can speak about this, but this is just to give you some overview. Overview on the applications of easy quantum groups. So originally there was a chapter 6, 7 or 8 planned, I guess. So now this is all collapsed in one chapter, since my schedule was a bit different in the end than what I thought. But okay, this happens. So let me first say a little bit how these easy quantum groups are related with the world of quantum groups. So what can easy quantum groups do for quantum group guys? So for quantum groups, first we've seen that it just gives rise to a class of examples. So this is of course one benefit one could have. So they give rise to many examples. So this is Wang's liberation and beyond. So by this I mean that Wang's original concept was you take a matrix quantum matrix group like Sn or On or Un, and then you try to make a free quantum version out of this. So this was what he did. And with these easy quantum groups, you see that you get many examples in this way when you have these non-crossing partitions. But if you have some crossings, then maybe this is not completely the liberation, so you don't lose all the commutativity relations, but at least you weaken them. So this is what I mean by and beyond. So this is still all in the spirit. Try to get rid of commutativity relations. And one machine could be take a result for Sn or On or Un, then prove it for Sn plus, On plus, Un plus, then you can prove it for all easy quantum groups maybe with the uniform proof, and then maybe for all compact matrix quantum groups or something like this. So this is somehow one hope that people have, okay? So you take such a result from the classical world. This is one step to the free quantum world, and then hopefully you find a uniform proof for all easy quantum groups, and maybe you see a structure that in the end you can prove it for all compact matrix quantum groups. I mean, if it's true. There are examples, yes. So I will tell you now 2 examples, but let me first say that in general the philosophy is that with these easy quantum groups, everything about the quantum group should be visible in the combinatorics. Okay, so hopefully you can have a lot of quite complicated operator algebraic properties, and you can express them in terms of the partitions. Maybe this is easier to understand. Philosophy. Every quantum algebraic property of an easy quantum group is visible in the combinatorics of partitions. And we have an example for this, which is somehow a mixed example for this one and also this other philosophy. Namely, this is take Sn G Hn infinity. So you take a quantum group which contains Sn and which is contained in Hn infinity, where Hn infinity is a quantum subgroup of Hn plus. And this is the easy quantum group associated to this category, which I gave last time. So last time we had the classification of easy quantum groups, and there were these non-hyperoctahedral ones. Then there were the hyperoctahedral ones containing this one, and the hyperoctahedral ones not containing this one. And so there's one quantum group, a hyperoctahedral one containing it, namely the largest one. This has this category, and the quantum group associated to it is called Hn infinity. And if I take any quantum group in between Sn and Hn infinity, which does not need to be easy, then we could also equivalently say we take any quantum group such that the Uij square are central projections. So when you write down what this category, what this partition means, this gives you exactly that the Uij square are central projections. So if I say I take any quantum group sitting between Sn and Hn infinity, I could equivalently say I just take any quantum group which sits in between Sn and On plus, such that the Uij are central projections. So if I take such a quantum group, then it is of the form.
Why are you squaring? Why is it squared?
This square comes from this fact. So here you have Uij, Uij, and here you have any other, and they should commute. And then it is of this form for some subgroup which is a quotient of this free product of Z2. So again, last time I said, what does this mean on the level of C-star algebras? On the level of C-star algebras, this means that this is isomorphic to C-star of gamma tensor CSN, but it's not the tensor product of these two quantum groups. It means that the Uij is exactly this element. Okay, so what
is gamma hat?
this is called semi-direct product.
Semi-direct product usually close one side.
Yeah, I think since here you act on both sides or something like this. I don't know if this is a good symbol, but this is the symbol that apparently is used. So if
Sorry, what will be co-multiplication here? I mean, it's not the tensor product, just the tensor product. The C-star algebra is the tensor product.
But C-star algebra is the tensor product, but the fundamental co-representation is this one. So for a tensor product, it would be the Uij's times VKL.
Sorry, what is that?
UGI. So here, so this gamma is a discrete group, so it has some generators GI. So these UGI, they generate this C-star algebra. And here I have some VIJs. And now the fundamental co-representation is UGI VIJ. So here it's twice the same I, which means it's not the tensor product, but it is somehow, yeah, it acts somehow this one acts on the group. This is why we have this. And the co-multiplication is then of course given just by the usual.
Tensor product somewhere, right? So when you say UGI, you mean UGI tensor VIJ.
Yes, yes. I always identify this with the C-star algebra generated by this and this, such that the elements commute, but maybe this is a cleaner way of putting it, yeah. So yeah, I don't know if people in group theory really use this. So I think the reference for this, I think it's maybe in Stefan Baas' paper or so. So I can look it up, but it's in this. This comes from the article with Sven Raum, and there we refer to the semi-direct product construction, and somehow I guess the idea is that you have something like this, but on the same time.
What is the later command for this?
I don't know.
Okay.
No, but
slash R times R cross, no, slash R times will give you the
Slash R times gives you this one, I guess, or maybe the other one, yeah. Yeah, but somehow I guess the understanding is that you, and at the same time you have this with this one and this symbol, but also this one. So this is, yeah, exactly, yes. Each acts on the other, because here you see somehow this Vij acts on this one. This is why we have the same I. Yeah. If you're not happy with this symbol, just take a look at the definition. And the definition is you take the tensor product of the C-star algebras and this fundamental representation. Yeah. Okay, but the point is that this theorem
C gamma hat tensor CS1
yes.
will be isomorphic to C, the maximal C-star algebra of gamma.
Yes.
Gamma is it an abelian group? It's an abelian group, right?
No, it's here. It's a quotient of this.
no, it's a free product.
It's a quotient of this free product.
Product is not abelian.
So then what is gamma hat means?
This means the dual. So
It means C-star max basically.
Okay.
yeah, it means this one. Yeah. So if you take any discrete group, this one will always be a quantum group, and the quantum group is seen as the dual of the discrete group. So it's written as this one. Yes, yes. Yeah. I didn't introduce the notation. That's true. Yeah. But this is somehow the standard notation people use in compact quantum groups.
And it's just the product, right?
No. One is commutative, the other one is co-commutative, so you can't take the tensor product anywhere.
Okay, so it's
Yeah. So if it would be the tensor product, then you would. Then here you would have maybe some k or something like this, right? So, but here it's the same I as here. Okay, but the point is here that this theorem disappeared when we classified the easy quantum groups. So I had this threefold classification: non-hyperoctahedral, hyperoctahedral not containing this one and containing it. And if it contained it, the statement was exactly of this form. So we proved this in the combinatorics by combinatorial means, but then we found out that this holds true for any compact matrix quantum group of this form, so also for non-easy ones. Okay, so this means, in this sense, this is a a proof for this one. Maybe if you restrict what I mean by all. But the point is that we had a uniform proof for the easy quantum groups. We had a result, and we saw that the result is true also for others. Of course, then you need a new proof. But so we have a new proof, and then we see that this holds true for any matrix quantum group. So this is an example where this philosophy is successful, first to study the easy case and then get a result for the others too. So this is generalized. Okay, and just for the experts, this isomorphism is only true if G is in its maximal version. So it can be in the full or reduced or something in between. So this is only true for the maximal version. Otherwise, it's a quotient of this one. But this is just a remark for those that know what maximal version means.
If you take the reduced here, maybe you can also get the reduced there.
Yes. So, yeah, maybe. You mean here, right?
Yeah.
Yeah.
And you have to take the minimal tensor product.
Yes.
I think you get,
Yeah, I didn't check it, yeah. Okay, so this is one example. Another example is the representation theory of easy quantum groups. This may be described in terms of partitions. Oh, I wanted to give the references, so this is in a joint work with Sven Raum. Okay, so here the representation theory. So usually the representation theory of quantum groups that is hidden in the fusion rules, and this means, what does it mean? It means find all maybe equivalence classes of irreducible representations. And second of all, so maybe we write it like this, and then we have to explain how the tensor product decomposes. Okay, so the representation theory, usually that is, you find all irreducible representations, and then if you take the tensor product, this gives a representation, and we know that it always decomposes into irreducible ones. Into which? That's the question. And if you can describe this, then this is called the fusion rules, and this is usually what you want to know for a quantum group. And here, for these easy quantum groups, we can do this on the purely combinatorial level. Okay. So maybe just to sketch it, so here, if G is easy with category C, we take partitions P that have the same number of points above and below, and they should look like a projection. So this means if I take the star, this is the same as P, this is the same as when I compose it twice with itself. Okay, you take a partition and you compose it with itself. That's another partition. Well, this should be P again. And then we define,
What do you mean PP equals P will have different points at the top and different
no,
number of
it's K is, in K is the same.
It's composable, sorry.
Yeah, yeah.
Got it, sensible. Yeah.
No, that's
Yeah.
composition, yeah. So you have K points here, K points here, and you compose P with itself. So for instance, if you take a look at this partition maybe, this would be projective. If you turn it upside down, it's the same partition again, and if you compose it with itself, then again, it's this partition. And for such a partition, this map TP this is then up to some normalization. This is a projection, because you know that the TP star is the same as T of P star, which is T of P. Okay, so it's self-adjoint, and also with the composition, there you have something with these blocks. But if you give a good normalization, then this works. So this will be a projection, and we take this projection and we subtract all projections which are closer, which are smaller. So we subtract the maximum or the supremum of all Q. We take all other projections. Let me call it projective. So having this relation such that P is smaller than Q is smaller than P in the usual sense. So we have something like this. So we take this projection and we subtract all these which are smaller, and this is a projection. So up to normalization. And this will give us a subrepresentation. Namely, we can apply this PP to U tensor K. But now this TP is an intertwiner. All these TQ are intertwiners. So this also intertwines with U tensor K. So this is the same as this, which means that if I view this as a matrix, then this will give me a block in this matrix. And this will tell me that this is a subrepresentation. This is a subrepresentation. And we can describe what is the tensor product of two of these guys. And this can be described explicitly. I'm always writing this, miswriting this word. Is it written in the correct form? Yes, I guess. Right, okay. I always feel that there must be some E, but whatever. Okay, so we have such a subrepresentation, and we can describe what is the tensor product. It will again decompose into such representations here, and we can control this set in a precise way. So now there's a problem. These UP, they are not irreducible. Okay, that's bad luck. So, because here for these fusion rules, we have to find all irreducible representations. If these UP were irreducible, then we would have the fusion rules on the partition level. Okay. So this means in some cases, namely for instance when our category is a non-crossing, only consists of non-crossing partitions. A sum of what?
I mean, I think at least in projections, do they sum up to 1? They're not.
Yes. So let me see. Yeah. Okay. So if I take something like this,
Yeah.
then I will get the full one. But they might not be orthogonal. That's a bit a problem.
Yeah.
but at least they sum up to 1, yes. So if now my category only consists of non-crossing partitions, then
What is it? What is it you're summing? Summing of UP?
summing over all my UP, where these P are in the category, and they are projective. So these UP that I defined here, when I sum over all these, I will get this one in the sense that
No, you don't have to.
they might not be orthogonal. This is what I have to point out at this point. Okay, but if my category only consists of non-crossing partitions, then in fact these UP are irreducible. We can also describe what are equivalence classes. So we satisfied A, and we satisfy the decomposition rule. So we can describe this via this XC. Okay. So. Otherwise, we just have somehow rough fusion rules. Okay, in the sense that these UP are not irreducible. But we have some refinement. So even if our category is not only non-crossings, then we have to refine this again and find smaller partitions, and we can do this. So we can really come to the point until we have all irreducible ones. But this is a bit nasty, and I don't want to write it down here. But maybe what one should see is that on this level of this partition fusion rules, if you want, we have a quite nice description. And in certain cases, this is all that we want to have.
So, sorry.
Yes.
What is the fusion rules? What are the fusion rules of AO again? SU2, SU2 is it?
Yes. So AO for AO, they are indexed by natural numbers,
Yeah.
and then you have that UK tensor UL. This is UK exactly, and then always +2. This is for ON plus, and for SN plus, this is exactly the same but with +1.
Yeah. Right.
Yeah. And in fact, good remark. In fact, the fusion rules for SN plus, they have been computed by Barnica in the 90s, and also for ON plus. So this is known, but he proved it separately. And from our proof, you can deduce the fusion rules for SN plus and for ON plus, and you can explicitly get the results of Barnica, but we have a uniform proof. Okay, so in this sense, this is a bit more systematic. And if you want, just maybe to give you a very, very vague idea, that here we can explain that this +2, this comes from the fact that we have this partition in here, whereas here we also have this partition. So these k, these natural numbers here, so this is now a remark for the experts that know the fusion rules for ON plus and SN plus. These are indexed by natural numbers, and the natural numbers, they appear as the through strings of our partitions here. Okay, so here we have 0, so this would correspond to k equals 0. Here we have 1, which would correspond to k equals 1, and so on. And since we have these partitions in SN plus, which correspond to all non-crossing partitions, we have more possibilities here. So we in this sum, when decomposing UK tensor UL, you have more possibilities of partitions arising. So this is why we have here always this +1, whereas here it's a bit more restricted, so we only have +2.
Can you tell the dimensions also?
Of the subrepresentations?
Yeah. Of the irreducible.
I don't think that we have something for this in our paper. Yeah.
I don't think that is known also.
Yeah, yeah. Yeah, I don't know.
Is there any reason to believe that even if you have start remaining quantum field, that your irreducible will be describable in terms of particles?
Is there any reason for this? Yes. I mean, okay, the way how we came to it is, so we saw that whenever you take such a projective partition, you will get a sub-representation, just by defining this PP and having this intertwiner relation there. And now you could ask how many. Okay, so what could you ask? Let me see. Okay, so if you have, for instance, so I hope I will do this right now. But if you have, for instance, U2 tensor U2, and you're in the case of ON plus, then this will decompose as U0 plus U2 plus U4, and okay, there's a counting argument which I don't get right for. No, I guess it's something like this. Wait, let me see. So this is the same as U0 plus, yeah, exactly, yeah. So okay, so if I have U tensor U, then this is U0 plus U2. And now if I have U4, I can write it as U2 tensor U2, which is U0 plus U2 tensor U0 plus U2. And then you will get a full list. So this is something like these two together. This will give you U0. These two guys together, this will give you another multiple here plus U2. Then these guys together, they will give you something like 3, and here you have 2. And now for the last one, you will get this one again, this one, and this one. Just by following, what will be U0, U0, what will be U2 tensor U0, U0 tensor U2, and U2 tensor U2. So U2 tensor U2, this is U0 plus U2 plus U4, according to the fusion rules, which are known. So you have something like this. And now if you write down the partitions with 4 upper points, then you will see that you will have one with 4 through strings. You will have one, you will have this one, and this one, and this one, these 3. And for this one, you will have some 4 or something like this. So yeah. So you will see that the number of projective partitions, which have the same number of points above and below, this has exactly these numbers here. And then you can continue some games like this. So this gives you some evidence that these numbers that appear here, they have to do something with the partitions.
But this is an explicit model for the representation theory. Right?
Yes, exactly.
Then you can calculate the dimensions also.
Okay.
Yeah, and I don't think that is known.
Okay.
Yeah.
Okay. Maybe we should speak about this. I'm not aware how I should do this at the moment, but maybe that's possible, yeah. I don't quite know if this answers your question, but when you play around with these fundamental representations and the fusion rules, you will see that there's some evidence that this can be reflected in the partitions. And yeah, and then this is the explicit statement for this.
And you have these two strings
So you mean I have a crossing like this?
No, no. A cap above its cross and a cap below.
And a cap below.
No, this wouldn't work because you need this one. So if you flip it, if you turn it upside down, it must be the same. So if you take the star of this one, then it's this one, which is not the partition again. No. Okay, so there's some evidence that this can be reflected in the partitions, and in fact this is also the way how we started our work by discovering this one, and then we tried. Okay, then you have to write it the other way around in order to see that this is true in the end. But yeah. Okay, so if you're not so familiar with the fusion rules, maybe you should just know that this representation theory of these easy quantum groups, this can somehow be reflected in this partitions. And oops. Since I want to tell you a bit more, let me just say that a third example for this philosophy that all the properties can be seen in the combinatorics is that you can give the Haar state in a combinatorial way using the partitions. And this is the Weingarten Calculus developed by Benoit Collins and also Theobanica. So you can describe this Haar state with partitions. Unfortunately, this is not too explicit, so it's difficult to deal with it because you have a big matrix and at some point you have to invert it. But still, it can be done with the partitions. Oh yeah, this was the paper together with Amaury Frelon. I think this was also 2013. Okay. Let me give you a short list of properties of von Neumann algebraic properties of the factors associated to some easy quantum groups. So for von Neumann algebras, we know that, okay, so this is C-star algebras, but of course these are very much related to the von Neumann algebras. So these C-star algebras, they are non-nuclear, they are exact, and they are simple, and they have the matrix approximation property. So this is Barnica, Vaz Vernieu, and recently Michael Brennan. They did something for that. And then you can deduce that these factors, they are strongly solid, non-injective, full prime to 1 factors. They have the R group approximation property. They have no Cartan subalgebra. And we know that for LU2 plus, it's isomorphic to LF2. So these are the same guys as above. And Isono, and we also know that these quantum groups, they fulfill Baum-Kohn. So there's a Baum-Kohn conjecture also for quantum groups, and the K-theories are known. K-theories for On plus, Un plus, and Sn plus are known. So this is mainly Christian Vogt. Who did this? And they are also weakly amenable. They fulfill Aikman-Ostrand and rapid decay. Okay, so this is some list of properties. If you know what the single properties mean, maybe this means something to you. If not, then maybe just forget.
To be careful with the n because On plus. For 2 it is just SU minus 1, so it's like.
Okay, yeah. Okay, so there are always some dimension restraints. Yes?
These, the predictions that you write down, they seem to commute with the UIJs, right? So is there a connection? Is the computer of these phenomena algebras computers is these predictions making that is possible to
Nice question. I have no clue.
computers of these phenomena, these type of because he writes the relation that u tensor k.
You're
I don't know, that does not,
Hmm.
that seems, it seems to imply that,
I mean, this only means that these objects commute with some products, right? So not with all of these elements themselves, but still it might be that you can say something about the commutant, but I have no clue. Yeah. Okay, I mean, if you see this list, and if you're familiar with the free group factors, then you see that a lot of these properties also are fulfilled by the free group factors. So this is why some people believe that these factors are have something to do with the free group factors, but of course you would have to prove something like that. Or maybe at least, so what some people try to do is they try to check all the properties that are fulfilled for the free group factors now also for these ones, and maybe on the way you can learn something for the free group factors. Maybe at some point you will find a property which is not fulfilled for the free group factors. So there's a lot of open things, and you see that I only wrote it down for On plus and Un plus. Also little is known about Sn plus for some of these properties, but not much. And I think
I think the K theory is known
for Sn plus, yes, yeah, exactly, yeah. This is quite recent. But for other easy quantum groups, a lot of things are unknown. So if somebody likes quantum groups and likes von Neumann algebras, just go ahead and do this for the other easy quantum groups.
Oh, this is not known?
No, for many of these things, for the easy quantum groups, it's not known.
Some of them will follow because they're lying between.
That's true.
Most of them probably will follow like that. For example, exactness and non-nuclearity will also follow, I guess, in many cases.
Yeah, so
Simplicity might be hard.
so for many cases, if you take one which sits inside here, right?
Yeah.
But we also had other examples where you have this Hn plus, and then you have these quantum groups which are below, and for those things are not so clear, yeah.
Like in the group case, this is the hardest part, right?
Exactly, yeah. Because there you have some commutativity, and the question is if this this slight commutativity if this destroys properties or not. So that there are still some interesting things to be done. And of course, what we always want to have is a uniform proof for all easy quantum groups. Right? You do not specify the category, just
At least for the 7 non-crossing one, everything should be known, right?
yes. Yeah. I mean, I didn't check case by case, and also it would be nice to have a new proof, not proving it for Sn plus and On plus separately,
Yeah.
but for both in a uniform way. But yeah.
K-theory first.
Yeah. Okay. So for the K theory, we know all of these. Yeah.
Oh, really?
Yes. This is because these you had this Hn. Oh no, we don't know it. I guess we don't know it for Hn plus. Yeah. But some of the others, for instance, there was one which is called Sn prime plus, and this is just this one tensor Z2. So you can say what this is for the K theory. Okay, so I will just leave this list as it is. As I said, if you're interested, then here are some references. I would recommend a very good reference is by Michael Brennan from 2012, because there, I guess he lists more or less all of these properties, maybe not all of them, but many of them. So this is a good start to see these properties and maybe to see more precise the references. Okay, but let me for the now spend half an hour on free probability theory. Free probability theory. Because this is somehow definitely one of the origins for the easy quantum groups, because the easy quantum groups involves partitions, free probability involves partitions, so the link was somehow by construction. So let me tell you just a little bit about this. I assume that many of you don't know what free probability is, so let me motivate this a little bit. So the motivation is, first, the free group factor problem. So if I take two free groups and n not equal to m, then they are non-isomorphic. And of course, the same holds true if I pass to the group algebras. And I can even impose some analytic structure and do it for the reduced ones. This was done by Voiculescu. And once he was in this business of the reduced ones, he said, okay, let's take the von Neumann closure. And he wanted to work on this one. This is an old problem since the very early days of Murray and von Neumann. Murray and von Neumann, they introduced these factors, and they couldn't solve this problem. And since then, this is open. So if you want, I don't know, some 70 years or so. So this is still something which is open. And yeah, people might wonder if this von Neumann closure is so strong that it makes these two objects isomorphic or not. Okay, and this was somehow the starting point for Voiculescu to say, okay, I want to work on this thing, and let me see what does it mean that the group is a free group. Okay, we can say, let our first group, let it call Fn, and the next one is F2, and then we take G as the free group with n plus m generators. Then G1 and G2 are free inside of G, meaning that if you take a Gj, which is not the neutral element, And if you take elements from alternating groups, then the product is not the neutral element. Okay, so this means free. I take a product of elements. The first element comes from one of these groups, the second one from another, the first one again from the first one, and so on. So these are alternating. None of them is the neutral element. So how could I multiply them and get the neutral element? I cannot, because they are free. Okay, so if they are not free, they have some relations, and then it might be that some G1 cancels with G2 or something like this. But if they are free, this is the case. Okay, so in this sense, these two groups are free in this one. So let's see what this means on the group algebra level. So same is true for the group algebras. So these are also free in the sense that if I take now an AJ, which is in the group algebra, of course, given as such a finite sum, and we don't want to have the neutral element in the sum, so the coefficient of the neutral element should be 0. And again, they should come from different algebras. Then also the product does not contain the neutral element. Okay, so this is just a formulation for the group algebras. I take an element in the group algebra, the neutral element is not contained in the sum. I take the product, and now if I just do the summation for each summand, I see that I'm exactly in this case, so none of these products appearing here will contain the neutral element, so the coefficient of the neutral element will be 0. Okay, so we can describe somehow that these group algebras are free in this big one. But now let's jump to the von Neumann algebras. How can we do this there, right? I mean, take an element, say it does not contain the neutral element. What does this mean? Because here we can always have these finite sums, but in a von Neumann algebra, I mean, the idea is that it is not a finite sum, right? Okay, help comes by using the state. So we have by the trace state. So we have a trace state here on these group algebras, and this can help us to formulate it for von Neumann algebras. Namely, we can say that this is equivalent to saying that the state, the trace of AJ is 0. So where T is the trace, tau is the trace on CG, mapping just taking the coefficient of the neutral element. This is a trace state, and we can just say tau of this element should be 0, and here we can say tau of the product should be 0. Okay, so now we don't have any sums, right? It's just saying I take elements, tau of the element is 0, then tau of the product is 0. That's all. And this is the definition of freeness. So Voiculescu gave this definition in 85 or so. You take subalgebras, all containing the unit. A is a unital algebra. And we have some functional. then we say that these algebras are free. Okay, now this is the definition. If and only if we take AJs from algebras such that phi AJ equals 0, and they do not come from the same algebra, then the product should be 0. Okay, really this is just the analog of what I had over there, now with an arbitrary algebra and an arbitrary linear functional. And this A phi, this is called a non-commutative probability space. An algebra together with a functional. Why is this a non-commutative probability space? So what, now we understand the word free, but what is probability here? Okay, so probability comes into play by the following. Here? I of j's, so this is an index. So my AJ, yeah. So this, it just means indexing the algebras. Okay, so what is probability here? Okay, so you recall the machinery that I gave in the very, very first lecture. I said something, you take a space, pass to the functions over the space, and then turn this algebra non-commutative. Okay, let's do this with probability theory. So we take a classical probability space. And then A defined as the algebra of random variables and phi of x defined as the expectation. This is a non-commutative probability space. Okay, so this is very similar to the above structure. We take this classical probability space, we pass to the algebras, which means we take the algebra of random variables, and this expectation, this is a state, is a linear functional. So this really looks like above. We have a unital algebra, and we have a unital linear functional. Yet we don't have something like freeness, so this we don't have. But for the moment, we just have such an algebra together with a state. So in this sense, this really looks like something with probability theory. And what is independence? So what is independence? Independence means if x and y are independent, then phi of xn ym is the same as phi of xn phi of ym. Of course, this is not like a probabilist would define it. He would define it with some sets, and then something should factor and so on. But the effect on the level of this state phi is exactly this one. So, and what does it? Why is this now useful? This philosophy in our case? Well, we see that many distributions are governed by their moments. Okay, by these elements. So many distributions. So we have something like a distribution This is determined by these numbers here. For instance, the Gaussian. So if you take any distribution, you compute these phi of x to the n. So this is an n. If you compute it, and if it's the same as for the Gaussian, then you know it's the Gaussian. Okay, so this, in this sense, we can identify a distribution with this one. And so this is the distribution of x. And exactly like this, the distribution of x and y. This is these numbers phi of xn, ym. So this means if now my x and y are independent, these numbers that I need, they are given by these numbers, so this means they can be expressed in terms of the moments of x and y. So independence gives me a rule of computing these mixed moments by the single moments. And in fact, this is exactly what freeness does in the non-commutative sense. Mixed moments are expressed in terms of the single moments. Let me tell you what this means. So independence means that the distribution of x and y may be computed using the distributions of x and y. So maybe not using, but knowing. And this is in terms of moments. And the same is true for freeness. So for this, what I defined here. Namely, for instance, we can say let's take an element A from one algebra and an element B from another one. And let's take a look at this expression here. So A is from A, B is from B, and A and B should be free. So we have two free algebras, and now this element here, minus phi of 1, if I apply phi, I will get 0. Okay? Same is true here. If I apply phi, this is 0. So this means phi of the product is 0 by definition of freeness. And what does it mean? I just computed, so I have phi of AB minus phi of A, phi of B, minus phi of A, phi of B, plus the thing, so this is the result. And this means phi of AB equals phi of B. Okay, so if I know these moments, phi A and phi B, I know this moment. And now if I do the same thing, maybe a bit more complicated, likewise, maybe something like phi of AB, this is expressed using phi A square, phi B, and phi B square. Okay, you do the same trick, and then you can compute it. So all of the mixed moments, they are always expressed in terms of the single moments. So freeness is a rule to calculate mixed moments. So hands of joint distributions. Okay, so if I say the joint distribution of two elements, this is given by all these moments. Now freeness gives me a rule to compute it in terms of the single moments. Okay, so this is the idea of freeness, and this is why free probability is called free probability, because this is analog to probability theory. Okay. Just as a side remark, if you take a von Neumann algebra that is generated by some elements, you take another one which is generated by some elements, and if they have if they have faithful normal states and their distributions are the same, so these numbers here, then these two von Neumann algebras are isomorphic. So this means that this is not just playing around, but it really is somehow a tool to say when some von Neumann algebras are isomorphic. So I take two von Neumann algebras and I have two faithful states. And I have that phi of all expressions is the same as psi of the same expressions in the B's. Then these two von Neumann algebras are isomorphic. Okay, so this means that these moments here, this distribution, that is really something you want to know if you want to know that two von Neumann algebras are isomorphic. So in this sense, this freeness rule might help to get some isomorphisms of von Neumann algebras. So freeness is useful for isomorphisms, for finding isomorphisms of von Neumann algebras. Also, there's a link to random matrices. Here's no what?
That is all just faithful normal state.
Yes.
No freeness is it.
Yes, exactly, yeah. So this is just faithful normal states. So this is just for expressing that these moments, so these distributions, that's really something useful.
I'm asking whether the algebra generated by A over the A are demanded to be free in A.
No. It's here. What I'm saying here is just I have these von Neumann algebras, and I have that these moments are the same as these moments, and then they are isomorphic. So hence, it is interesting to know how do these moments look like, and since freeness is a rule to answer this question, it's a useful tool. So this means in certain cases, if you have some freeness involved, then maybe you can write this in terms of other moments, and then you might have something like this, and then you might have the isomorphism. So there's a link to random matrices, namely large random matrices behave like free elements. So this was somehow the breakthrough for free probability theory. You have the link to von Neumann algebras, but you also have the link to random matrices. So this is something in classical probability theory, but if you have large random matrices, so this is a matrix where all the entries are random, plus some extra structure. And if you have such things, and if they become larger and larger, they really behave like elements in free probability. So you can predict some results on large random matrices by using free probability theory tools. And often large means n equals to 8. So it's the real world. It's not 10,000. So this is nice because now we also have a random matrix tools for von Neumann algebras. And for instance, using this, Voiculescu could show that the free group factors have no Cartan subalgebras or something like this. So you can prove some theorems about von Neumann algebras by using random matrices. And furthermore, there are links to many other parts in mathematics, namely links to combinatorics, complex analysis, wireless communication theory, and quantum groups. Okay, so what's the link to quantum groups now? I should really tell you how this works together. But before doing so, let me quickly sketch very briefly how do the non-crossing partitions come into play for free probability theory. So this is now really, you get a half an hour crash course in free probability theory, so a lot of things will be not so clear, but you should just get maybe some ideas of how this works. So you have something like a theorem of Speicher from the 90s, namely such a moment. So these are the objects that we're interested, because this gives us the distribution. So this can be decomposed into sum of some numbers kappa p, and these numbers are indexed by non-crossing partitions. And these are called cumulants. Okay, so far this is just, if you know a bit about combinatorics, this is not so surprising that you can do something like this. But okay, it's free cumulants. But now the theorem is so two algebras are free if and only if kappa p of these things is 0 if you have one coming from one of these algebras and another one from another one. So this is referred to as vanishing of mixed cumulants. Okay, so this is a nice description. Okay, so when we had this definition of, sorry? No, A1 and A2, or what do you mean?
The statement is that if the cumulant, mixed cumulant can be non-zero only if they all come from the same number.
Ah, I see.
Yes.
And they don't have the alternating or anything.
No alternating thing. Yeah. So here, so this is really simplification, right? Because here you had this rule with this alternating things and so on, and this was a bit complicated. But in fact, here we say, so we can decompose such a thing in these with these numbers kappa p, and now if I take these kappa p and the entries, if I at least have one coming from one algebra, another one from another one, then this must be 0. So this is much easier to check. And this is a quite combinatorial description of freeness. And this is in terms of non-crossing partitions, and very often, so in classical probability theory, you have somehow a similar statement with all partitions here. So now we have it with non-crossing ones, and very often we have something like, if we go from all partitions to the non-crossing ones, this is equivalent to the step from classical probability theory to free probability theory. Okay, so this is a meta theorem, but this very often this is true that if you take a classical statement, you express it somehow in terms with partitions, and then you restrict to the non-crossing ones, you have a statement for free probability. And this is finally exactly what happens for the theorem of Divinity type. Namely, we have a theorem by Divinity from the 30s saying that if you take classical random variables so just random variables, and of course they commute because this is just a random variable, so functions, complex valued functions. And if the distribution of x1 to xn is invariant under Sn for all n, then this sequence is IID. Over the tail sigma algebra, sigma tail, which is like that. Yes, yes. So the conditional expectation onto this one. If you don't know that much what this means, take this as a detail now, okay? So what the statement should be, the distribution of a finite part of the sequence, if this is invariant under the action of Sn, so by permuting it, then the sequence is IID. And this is equivalent. And now we do exactly the same for the quantum groups, and we will get freeness. And this was by Klaus Köstler and Roland Speicher from 2009. And this is if you take elements in a non-commutative probability space A phi, and if now the distribution is invariant under, of course we should take the quantum version, so Sn plus, then this sequence is free identical distributed over, now the tail sigma algebra becomes the tail von Neumann algebra. Okay, so you have some.
What do you mean by distribution of x1, x2, xn for an n tuple of elements in A?
So this means I take moments, so I take products only in terms of these things. So I take arbitrary long products, but I can only involve these elements. Of course, I don't tell you something about the proof. I don't tell you exactly what this distribution is invariant under Sn plus and so on. So there are a lot of things which you don't understand when you see the proof. But what should be seen here is I take the group Sn, I have something, and I have classical independence, and here I have the quantum group, and I get freeness. Okay, so in this sense, if you're asking for distributional symmetries in free probability theory, you should not take groups, you should take quantum groups. Okay, so this is the thing you should get out of this half of the blackboard.
Are there any similar statements when you replace Sn plus by other quantum groups?
Yes. So here, for instance, if you take On, you will get the Gauss. So they are not only this one, but they are also Gaussian. And here, if you take On plus, then you will get here the semicircle, which is the replacement of the Gauss in the free world. So this paper is only for Sn plus, but then there's also another one of Banica, Kern, and Speicher. Is it 2010? It's a bit later. And this is also something with Definetti for easy quantum groups, or something like this is the title. And there you will also have On plus and Hn plus and some others.
What is patient name?
Steve Curran.
And what about the easy ones?
I mean, On plus is easy, Hn plus.
But they have like similar statements for.
You mean a uniform one?
Yeah.
No, that would be nice to have. Yeah, I mean the proof they have is pretty uniform for 4 cases, but they have some restrictions. So they take an arbitrary category, but they say it must be non-crossing and it must be block stable. So if you remove one of the blocks, then the partition must still be in the category. And there are only 4 categories which satisfy this. Yeah. Okay, I guess this is all I wanted to tell you about applications of easy quantum groups, and also this is all I wanted to tell you in this lecture. So thank you very much for coming to the lectures.